Okay, the basic probability rules. Let's get some basis for some formulas here so we don't have to do these simulations and heroically take 20,000 trials to find the actual probability of something. Even then, we're estimating, right? Unless you're imprisoned in World War II and you do 40,000 trials, then you're really good. I mean, you're a hero. You're a hero. The probability of any event is always going to be a number between 0 and 1. It can be 0, it can be 1. That's what inclusive means. Part A, if the probability of an event is actually 0, it never happens. It can't possibly happen. It does not happen. If the probability of an event is 1, it always happens. So 0 is less than or equal to the probability of event A happening, which is less than or equal to 1. There's our first truth, formula-wise, about probability. All outcomes in the sample space must have probabilities that add up to 1. If we found the probability of every one of those rolls of dice, the 1 and the 2, the 2 and the 2, the 3 and the 5, all of those have a probability of 136. And if you add them all up, you will get 36 out of 36. If all outcomes are equally likely, the probability of event is event A, like rolling a 7. We found 6 different ways you could roll a 7, so it went 6 out of the 36 possibilities. That's how you find a probability right there. The probability that an event does not occur. This is the complement idea. It's called a complement. We just saw it on the last page. There are actually a couple of tricks we just saw on the last page you didn't even notice. This is a 1 minus. It's a 1 minus the probability that it does occur. So we had that 1/6 situation. The probability of the complement was 1 minus 1/6 is 5/6. So a complement is going to be denoted by this author as A with an exponent of C. That means complement. So if A is the event, the sum of these two dice is 5, then A complement, that's the notation we're just working with, is that the sum is not 5, like we just saw on the last page. Okay, so if the probability of A is 1/9, then the probability of A complement has to be 8/9, right? Or, as a formula, here's formula number 2 for you. The probability of A complement will always be 1 minus the probability of A. Hey, we're moving now. No simulations today. You don't have to be a hero to do this. You can just follow a formula. Now, here's a definition for you. If two events have no outcomes in common, the probability that one or the other one occurs is simply just the sum of their individual probabilities. You're allowed to add probabilities if you're looking for the word or in your problem, and there's no way they can happen at the same time. They don't have anything in common. Now, here's a definition for that. Events that don't have anything in common, that can't happen at the same time, they are called mutually exclusive events. You may have heard that term before because it's starting to get more popularly used in everyday language. Mutually exclusive means can't happen at the same time. People usually say it conversationally as things not being mutually exclusive, right? Like Piper and smart. Those two things are not necessarily mutually exclusive because every now and then the kid has an idea. Okay, so this says are, but this should say the word or. I'm making fun of Piper and I can't spell a 2-letter word. Mutually exclusive, or there's another word for it. I hate this, but we do actually have 2 different terms that mean the exact same thing. You gotta hate that too. I'd like to just know one or the other, but there's no difference between those 2 phrases. They mean the exact same thing. It means the 2 events don't have anything in common. Okay, so here's your first real formula. Put on your big boy pants. If A and B are disjoint, which means they don't have anything in common, the probability of A or B is simply equal to the probability of A plus the probability of B. Now, there's a big if here. If they're disjoint, you can't just go adding probabilities together if they're not disjoint. And I'll show you why in one of the next pages. But I'm going to go back a page, and I'm going to show you that we already used this. You ready for this? The probability that the sum was a 3 or a 4. Well, 2 of them were 3, and 3 of them were 4. And you can't possibly roll the dice and somehow get a 3 and a 4 at the same time, right? So what we did is we found the 3s and we found the 4s, and when we added them, we got 5 out of 36. Now, we didn't do that on your page because, I don't know why, maybe I'm just a loser. Here is your page. We just looked at it and counted them. We counted the 3s and the 4s, and then we added that. The other one's my cheat sheet. Okay, so there is your first formula for probability involving two things. We're going to add them together. All right, let's go to the next page.